The grandfather paradox. Let's start with the time traveler's most infamous headache. It's the one you've heard about, the one that supposedly makes a mockery of causality. The grandfather paradox. The premise is deceptively simple. You, a brilliant and slightly reckless inventor, build a time machine. Your mission? To travel back to the past and correct a historical injustice, or maybe just to see what the 1920s really smelled like. But while you're there, you run into your own grandfather, back when he was a young, single man. For some terrible, nonsensical reason, maybe you trip, maybe you have a vendetta against his questionable fashion sense, you cause his untimely demise. He dies before he ever meets your grandmother. Here's where the logic starts to eat itself. If your grandfather dies, he never has children. Your parent is never born. And if your parent is never born, well, you certainly aren't. You are wiped from the timeline, but if you were never born, you could never have built the time machine in the first place. You couldn't have traveled back to do the deed. So, your grandfather lives, meets your grandmother, and you are eventually born, which means you can build a time machine and go back and... You see the problem. It's an infinite loop of contradiction, a causal loop that spins on itself until reality shorts out. Every effect requires a cause, but here the effect seems to erase its own cause. So, is time travel into the past impossible? Is the universe protected from this kind of chronological vandalism? Physicists have a few potential escape hatches. The first is the most brutally simple, the Novikov self-consistency principle. This idea, proposed by Russian physicist Igor Dmitrievich Novikov, essentially states that the universe is pathologically self-consistent. Paradoxes are not allowed. You can travel to the past, but you are physically incapable of changing it in a way that creates a contradiction. The gun you point at Grandpa will jam. You'll slip on a conveniently placed banana peel. You'll suddenly have a profound change of heart and decide he's not so bad after all. The laws of physics would conspire in increasingly absurd ways to ensure the timeline remains intact. The past is a fixed, unchangeable block. You can visit it, but you can't re-sculpt it. You're a tourist, not a god. But that's no fun. A more tantalizing solution is the many worlds interpretation. Popularized by physicist Hugh Everett, this theory suggests that every quantum event creates a branching point in reality. Every possibility happens, just in a different, parallel universe. In this model, when you travel back and dispatch your grandfather, you don't erase yourself from your original timeline. Instead, you create a new one. You've just cleaved off a divergent branch of reality, a timeline where you will never be born. You, however, are now a temporal orphan, a refugee from a timeline that still exists, but to which you can never return. You've successfully murdered your grandfather and created a world devoid of you, but you are still very much real, stuck in the alternate past you created. This neatly resolves the paradox, but it does so at the cost of creating an infinite number of parallel universes and stranding you in one of them. Choose your poison. The Fermi paradox. Look up at the night sky. It's vast, unimaginably vast. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. Many of those stars have planets. Many of those planets are likely in the habitable zone, where conditions could be right for liquid water and therefore life as we know it. The universe has also been around for 13.8 billion years. Given all of that, the sheer number of chances, the unimaginable stretches of time, the math seems to suggest that intelligent, spacefaring civilizations should be common. They should be everywhere, and yet when we point our radio telescopes to the heavens, we are met with a profound, deafening silence. This cosmic quiet is the heart of the Fermi paradox, a question famously blurted out by physicist Enrico Fermi over lunch in 1950. Where is everybody? If even a tiny fraction of those billions of stars gave rise to intelligent life, and a tiny fraction of those developed interstellar travel, the galaxy should have been colonized millions of years ago. A civilization just a little more advanced than ours could send out self-replicating probes that could visit every star system in the galaxy in a few million years, a cosmic blink of an eye. They should have left signals, structures, or at the very least, some cosmic garbage for us to find. The absence of this evidence is the paradox. The numbers say the sky should be crawling with aliens, but the evidence says we are utterly alone. So, where are they? This question leads to a series of chilling and fascinating possibilities known as the Great Filters. A great filter is a hypothetical barrier or challenge that is so difficult to overcome that it prevents almost all life from reaching an advanced interstellar stage. The paradox is that we don't know if this filter is behind us or ahead of us. Possibility 1. The Great Filter is behind us. We are the first. The filter could be the origin of life itself. The leap from non-living chemistry to a self-replicating organism might be so freakishly improbable that it has only happened once. In this scenario, we are the universe's first and perhaps only shot at consciousness. We are monumentally special and monumentally alone. Possibility 2, the terrifying one. The Great Filter is ahead of us. Life might be common, intelligence might be common, but something always, inevitably, prevents civilizations from going interstellar. What could it be? Self-destruction is a popular candidate. Civilizations might always develop technology that outpaces their wisdom, leading to nuclear war, runaway climate change, a Grey Goo nanotechnology disaster, or a malevolent super AI that turns its creators into paperclips. If this is true, the silence of the cosmos is a warning. We are approaching a wall that no one has ever survived. Other, less apocalyptic solutions exist. The Zoo hypothesis suggests that advanced aliens are out there, but they're deliberately hiding from us, treating Earth like a protected nature preserve. They are observing us from afar, following a strict non-interference policy. We are cosmic zoo animals. Or perhaps the dark forest hypothesis is correct. In a dark forest, you don't shout to announce your presence, you stay quiet because you don't know what predators are listening. In this terrifying model, the universe is full of life, but everyone is hiding. Broadcasting your location is cosmic suicide, an invitation for a more advanced, more paranoid civilization to eliminate you as a potential future threat. The silence, then, is not emptiness, it's fear. Olbers' paradox. Here's a question that sounds like it belongs in a kindergarten classroom, but it has puzzled astronomers for centuries, and its solution reveals the very nature of our universe. Why is the night sky dark? It's called Olbers' paradox, named after the 19th century German astronomer Heinrich Olbers, though others had pondered it long before. The logic goes like this. Assume the universe is infinite in size, has existed forever, and is filled with a roughly uniform distribution of stars. If that's true, then no matter where you look in the sky, your line of sight should, eventually, end on the surface of a star. Every single point in the night sky should be occupied by a star. Think of it like being in an infinitely large, infinitely old forest. No matter which direction you look, you'll see a tree. If every line of sight ends on a star, the entire night sky should be a blazing, continuous sheet of light, as bright as the surface of our own sun. There should be no darkness at all. Day and night would be indistinguishable, both seared by the light of infinite stars. And yet we know this is not the case. We can see blackness between the stars. We have night. This simple observation directly contradicts the idea of an infinite, static, and eternal universe. So, what gives? The solution to this paradox is one of the most powerful pieces of evidence for the Big Bang and our modern understanding of cosmology. The faulty assumptions were that the universe is infinitely old and static. It is neither. Firstly, the universe has a finite age. It hasn't existed forever. It began approximately 13.8 billion years ago in the Big Bang. This means we can only see the light from stars and galaxies whose light has had enough time to travel across space and reach us. Light from a star that is 20 billion light-years away simply hasn't arrived yet. The observable universe is a sphere with us at the center, and its edge is defined by the distance light has been able to travel since the beginning of time. There are countless stars beyond that edge, but their light is still on its way, so their patch of sky appears dark to us. Secondly, and perhaps more importantly, the universe is not static. It is expanding. And it's not just expanding, the expansion is accelerating. This was Edwin Hubble's revolutionary discovery in the 1920s. He observed that distant galaxies are all moving away from us, and the farther away they are, the faster they are moving. This expansion has a profound effect on the light traveling from those galaxies. As space itself stretches, it stretches the wavelengths of the light traveling through it. This is called cosmological redshift. Light from the most distant galaxies is stretched so much that its wavelength is shifted out of the visible spectrum into the infrared and microwave parts of the spectrum. Their light is still arriving, but it's invisible to our eyes and carries far less energy. The most distant objects are receding from us so fast that their light will never reach us at all. So, the night sky is dark because the universe had a beginning, and because the space between us and distant stars is constantly stretching, robbing their light of its energy, and in many cases preventing it from ever reaching us at all. The darkness is the ghost of the Big Bang and the shadow of cosmic expansion. Schrödinger's cat. It is, without a doubt, the most famous and criminally misunderstood thought experiment in all of science. It involves a cat, a box, a bit of radioactive material, and a whole lot of quantum weirdness. This is Schrödinger's cat, and it pits our common-sense reality against the bizarre rules of the subatomic world. The setup, conceived by physicist Erwin Schrödinger in 1935, is a form of diabolical Rube Goldberg machine. You place a cat inside a sealed, windowless box. Along with the cat, there is a tiny amount of a radioactive substance. The amount is so small that in the span of 1 hour, there is exactly a 50% chance that one atom will decay, and a 50% chance that none will. This is a purely random, quantum event. Next to the atom is a Geiger counter. If the counter detects radiation from a decayed atom, it will trigger a hammer. The hammer will smash a small vial of hydrocyanic acid, a deadly poison, which will be released into the box and kill the cat. If the atom does not decay, the hammer is not triggered, the vial remains intact, and the cat remains happily alive. Now you close the box and wait 1 hour. According to our everyday intuition, the cat inside the box is either alive or dead. We just don't know which until we open it. But this is where quantum mechanics throws a wrench in the works. According to the Copenhagen interpretation, the dominant view of quantum mechanics at the time, until it is measured or observed, the radioactive atom is in a strange state called a superposition. It is not decayed or undecayed. It is simultaneously both decayed and undecayed in a haze of probability. But because the cat's fate is inextricably linked to the state of the atom, this implies that the cat too must be in a superposition. Until the box is opened and the system is observed, the cat is both 100% alive and 100% dead at the same time. Schrödinger did not propose this because he was a monster who hated cats. He proposed it to show how absurd he found the Copenhagen interpretation to be. He was trying to illustrate the ridiculous consequences of applying quantum superposition, which works for tiny particles like atoms, to a large macroscopic object like a cat. How can something be both alive and dead? It offends our sense of reality. The act of observation, in this view, is what forces reality to choose. The moment you open the box, the wave function of the system collapses, the superposition is broken, and the cat is instantly resolved into a single, definite state, either alive or dead. But what constitutes an observation? Does it have to be a conscious human? What if a mouse was in the box? Would that count? This is the measurement problem, and it's a deep mystery. The many worlds interpretation offers a way out. It says the wave function never collapses. Both outcomes happen. When the atom enters its superposition, the entire universe splits in two. In one universe, the atom decays, the poison is released, and the cat is dead. In another parallel universe, the atom does not decay and the cat is alive. Opening the box doesn't cause reality to choose. It simply reveals which branch of reality you happen to be on. In both cases, the cat is never a zombie-like mixture of alive and dead. The paradox is dissolved, but the price is a constantly branching, ever-multiplying cosmos of parallel realities. The twin paradox. Time, we intuitively feel, is absolute. A minute for you is a minute for me, no matter where we are or what we're doing. Albert Einstein's theory of special relativity blew that idea to smithereens. It revealed that time is relative. It can stretch and shrink depending on how fast you are moving. This leads to one of the most mind-bending but experimentally verified paradoxes, the twin paradox. Here's the scenario. We have a pair of identical twins. Let's call them Alice and Bob. Alice remains on Earth, living a normal life. Bob, the more adventurous twin, hops into an advanced spacecraft and blasts off on a journey to a distant star. His ship travels at a significant fraction of the speed of light, say 99% of it. He travels for a few years, turns around, and flies back to Earth at the same incredible speed. According to special relativity, something very strange will have happened. Because Bob was moving so fast, time for him will have passed more slowly than it did for Alice. This phenomenon is called time dilation. When Bob steps out of his spacecraft, he will have aged only a few years, but he will find that his twin sister Alice, along with everyone else on Earth, has aged several decades. Bob has effectively traveled into the future. This much is a solid prediction of physics. It has been confirmed with ultra-precise atomic clocks flown on airplanes and satellites. But here's where the paradox comes in. Think about it from Bob's perspective. As he was flying through space, he was stationary inside his ship. From his frame of reference, it was the Earth that zoomed away from him at 99% the speed of light and then came zooming back. So, if all motion is relative, shouldn't time have slowed down for Alice? Shouldn't Bob return to find a sister who is younger than him? Both twins see the other as the one who is moving, so both should predict the other will be younger. This is a clear contradiction. Who is actually younger and why? The solution lies in a crucial detail that breaks the symmetry of the situation: acceleration. Special relativity, in its basic form, only deals with inertial frames of reference, that is, objects moving at a constant velocity without accelerating. Alice on Earth stays in a single, more or less inertial frame the entire time. Bob, however, does not. To begin his journey, he must accelerate to an enormous speed. To turn around at the distant star, he must decelerate, reverse direction, and accelerate again. Finally, to land back on Earth, he must decelerate to a stop. It is this acceleration that makes all the difference. By accelerating, Bob switches between different frames of reference. This breaks the symmetry between the twins. There is now an objective, physical difference in their journeys. Alice experienced no significant acceleration, while Bob was subjected to immense forces. It is the traveling twin, the one who accelerates, who will always experience less time. There is no contradiction. It is a veridical paradox, meaning a situation that produces a result that seems absurd but is nevertheless demonstrably true. If you want to stay young, the trick isn't a better skincare routine, it's finding a spaceship that can handle a few Gs. Zeno's paradoxes. Let's take a walk. Or let's try to. An ancient Greek philosopher named Zeno of Elea would argue that this simple act is a logical impossibility. Zeno created a series of paradoxes around 450 BC that were designed to show that our common sense understanding of motion, space, and time is riddled with contradictions. The most famous of these is the dichotomy paradox, or the race course. Imagine you want to walk from one end of a room to the other. To get to the other side, you must first travel half the distance. No problem. But to travel that remaining half, you must first travel half of that distance, a quarter of the total. And to cover that quarter, you must first cover an eighth, and then a 16th, a 32nd, and so on. The problem is that this process of halving the distance can continue forever. You can divide any distance an infinite number of times. Therefore, to reach your destination, you must complete an infinite number of smaller journeys. You must traverse an infinite number of points. And how can anyone complete an infinite number of tasks in a finite amount of time? It seems impossible. Zeno concluded that motion must be an illusion. You can never truly reach your destination because you can never even take the first step. Another famous version is Achilles and the tortoise. The swift-footed warrior Achilles is in a race with a slow-moving tortoise. Being a good sport, Achilles gives the tortoise a head start. Zeno argues that Achilles can never overtake the tortoise. Why? Because by the time Achilles reaches the tortoise's starting point, the tortoise will have moved a little bit farther ahead. By the time Achilles covers that new, smaller distance, the tortoise will have moved ahead just a little bit more. This continues infinitely. Achilles is always closing the gap, but he never closes it completely because the tortoise is always creating a new, ever smaller gap to cross. These paradoxes stumped philosophers and mathematicians for over 2,000 years. They poke at a fundamental discomfort we have with the concept of infinity. Our brains are not wired to intuitively grasp it. The solution, which didn't arrive in a complete form until the development of calculus in the 16th century, lies in understanding that an infinite series can have a finite sum. Yes, the journey across the room is composed of an infinite number of smaller segments, but these segments become progressively, infinitesimally smaller. So, if you take the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 and continue that pattern forever, it doesn't add up to infinity. It perfectly converges to exactly 1. Similarly, the time it takes to cross each of these infinite segments also becomes infinitesimally small. The sum of this infinite series of time intervals is a finite amount of time. So, you can complete an infinite number of tasks in a finite time, as long as the tasks get smaller and smaller, faster and faster, according to a convergent series. Zeno's paradoxes don't prove that motion is an illusion. They prove that our everyday intuition about infinity is wrong, and that reality operates on the logic of calculus, whether we like it or not. The bootstrap paradox. This paradox is a favorite of science fiction writers, and for good reason. It messes with our fundamental notion of origin and creation. It's also known as a causal loop or an ontological paradox, and it describes an object, a piece of information, or even a person that has no beginning. It exists in a self-contained loop with no discernible point of origin. It just is. Here's the classic example. A man obsessed with Beethoven travels back in time to the 18th century, eager to meet his hero. He brings with him all of Beethoven's sheet music. But when he arrives, he discovers to his horror that there is no one named Ludwig van Beethoven. The man never existed. Panicked that a world without Beethoven's Fifth Symphony is not a world worth living in, the time traveler decides to publish the music himself under the name Ludwig van Beethoven. The music becomes famous, revered for centuries, and eventually inspires the very time traveler who brought it back in time in the first place. So the question is, who wrote the music? It wasn't Beethoven, he never existed. It wasn't the time traveler, he just copied it. The music seems to have appeared from nowhere. It is its own cause. This is the bootstrap paradox. The bootstrap metaphor comes from the idea of pulling yourself up by your own bootstraps, doing something impossible. In this case, the information has no creator. It's a closed loop, an informational free lunch. It gets even weirder when you apply it to physical objects. Imagine an inventor builds a unique, one-of-a-kind pocket watch. He then gives this watch to his younger self via time travel. His younger self keeps the watch his whole life and then, as an old man, gives it to his own younger self, who then... You get the picture. The watch is passed down through a loop. So, who built the watch? When was it manufactured? The watch seems to have existed forever, never being made, only being passed along. This runs into some serious problems with physics, particularly the second law of thermodynamics. This law states that entropy, or disorder, in a closed system always increases. The pocket watch would get scratched, its gears would wear down, it would accumulate entropy over time. An object that exists in an infinite loop should be an infinitely degraded pile of rust and dust. The fact that it exists in a pristine state is a physical impossibility. The paradox suggests that either this kind of causal loop is forbidden by the laws of physics, or that our understanding of causality and information is fundamentally incomplete. Perhaps in the strange logic of time travel, information doesn't always need an author. It can simply be found, floating in the currents of a looped timeline. The black hole information paradox. For the last half-century, theoretical physics has been dominated by two incredibly successful but mutually incompatible theories. General relativity, Einstein's theory of gravity, describes the universe on a grand cosmic scale: planets, stars, galaxies, and black holes. Quantum mechanics describes the universe on the tiny, bizarre scale of atoms and subatomic particles. Each works perfectly in its own domain. The black hole information paradox is what happens when you try to force these two theories into the same room. The result is a fundamental contradiction that threatens to break physics itself. Here's the setup. According to general relativity, a black hole is an object with such immense gravity that nothing, not even light, can escape once it crosses a boundary, called the event horizon. It's a one-way trip. Now, let's bring in quantum mechanics. One of the core, unshakable tenets of quantum theory is that information can never be destroyed. The physical state of every particle that makes up an object, a book, an astronaut, a planet, contains information. You can burn the book, but the information about its constituent atoms is still there, encoded in the smoke, ash, and heat. You can scramble it, but you can never erase it from the universe. So, what happens when you throw a book into a black hole? The information contained in that book, the story, the chemical makeup of the ink and paper, everything, crosses the event horizon. According to relativity, it's gone forever, locked away from the rest of the universe. But in the 1970s, Stephen Hawking made a startling discovery. By combining quantum effects with relativity, he showed that black holes are not completely black. They slowly leak radiation, now known as Hawking radiation, over immense periods of time. This leakage causes the black hole to lose mass, and eventually, after trillions upon trillions of years, evaporate completely, leaving nothing behind. And here's the paradox that has tormented physicists for decades. If the black hole evaporates, what happened to the information from the book you threw in? Is it destroyed forever? If so, quantum mechanics, a pillar of modern science, is wrong. Does the information escape somehow, carried away in the Hawking radiation? If so, general relativity's description of a black hole as an inescapable prison is wrong. You can't have it both ways. It's a fight to the death between our two best theories of reality. This isn't just an abstract puzzle, it's a central crisis in the quest for a theory of everything. Proposed solutions are mind-bending. One idea is that the information is, in fact, encoded in subtle quantum correlations within the seemingly random Hawking radiation, like a secret message hidden in static. Another, more radical proposal is the holographic principle. This suggests that all the information about the three-dimensional interior of the black hole is actually stored on its two-dimensional event horizon, like a hologram. The book never really goes in. Its information is smeared across the surface. This idea has been extended to the entire universe, suggesting that our 3D reality might just be a holographic projection of information stored on a distant 2D surface. The paradox, then, isn't just about black holes, it's a clue that our entire conception of space and reality might be an illusion. The observer's paradox. You can't measure something without changing it. This is the simple, frustrating truth at the heart of the observer's paradox. In social sciences, this is a well-known problem. If you want to study how people behave naturally, you have to watch them. But the very act of watching them makes them aware they are being studied, causing them to change their behavior. They become self-conscious, they try to act in a way they think the observer wants to see. You can never observe the purely natural state because your observation contaminates it. But when we dive into the quantum realm, this paradox takes on a much deeper, weirder, and more fundamental meaning. It's not about consciousness or psychology, it's baked into the fabric of reality itself. This is the observer effect in quantum mechanics. At the subatomic level, particles like electrons don't exist as tiny, definite points. They exist as a wave function, a fuzzy cloud of probability representing all their possible locations, speeds, and other properties at once. The electron is not in any one place, it is in all possible places simultaneously. The paradox arises when you try to measure it. To find out where the electron is, you have to interact with it, for example, by bouncing a photon of light off it. The moment you do that, the moment you observe it, the wave function collapses. The cloud of probability vanishes and the electron is forced to pick a single definite location. The very act of measuring its position has fundamentally altered its state, changing it from a wave of potential to a definite particle. This leads directly to Heisenberg's uncertainty principle, which states that there is a fundamental limit to how precisely you can know certain pairs of properties of a particle at the same time. For example, the more precisely you measure an electron's position, the less precisely you can know its momentum, and vice versa. It's not because our measuring instruments are clumsy. It's a fundamental property of the universe. Reality itself has a built-in fuzziness. You can ask, "Where is the particle?" and get an answer. Or you can ask, "How fast is it moving?" and get an answer. But you can never get a precise answer to both questions at the same time. Observing one property inherently scrambles the other. This is profoundly strange. It suggests that at the most fundamental level, reality is not a fixed, objective thing just waiting to be discovered. Instead, it is a participatory process. The properties of the universe are not defined until they are measured. This raises the same troubling questions as Schrödinger's cat. What counts as a measurement? Does it require a conscious observer? Or does any interaction with the environment count? The observer paradox in quantum physics tells us we are not passive spectators of the universe. We are intrinsically part of the system, and our attempts to know reality inevitably help to create it. The simulation argument. We end with the grandest, most existentially terrifying paradox of them all. A paradox that doesn't just question a law of physics or the nature of time, but questions the very nature of reality itself. This is the simulation argument, most famously articulated by philosopher Nick Bostrom. It doesn't claim that we are living in a computer simulation. It claims that one of three very different propositions is almost certainly true, and two of them are bleak. Here is Bostrom's trilemma. At least one of the following statements must be true. Proposition 1, the doomsday scenario. Civilizations at our level of technological development almost always go extinct before they are capable of creating ancestor simulations, ultra-realistic, high-fidelity simulations of their evolutionary past, populated by conscious, simulated beings. This is another version of the Great Filter. We will be wiped out by war, plague, AI, or some other catastrophe before we ever get to the simulation building stage. Proposition 2, the apathy scenario. Advanced post-human civilizations that do reach technological maturity have absolutely no interest in running ancestor simulations. Perhaps they find it unethical to create simulated consciousness that can suffer. Perhaps they have moved on to more profound forms of existence and find simulating their grubby past to be utterly boring. For whatever reason, they have the capability, but they universally choose not to use it. Proposition 3, the simulation scenario. We are almost certainly living in a computer simulation. The logic is starkly statistical. Let's assume that propositions 1 and 2 are false. That means that civilizations do survive to a post-human stage, and they do run lots and lots of ancestor simulations. A single one of these advanced civilizations could run billions or trillions of simulations of their past, each containing billions of simulated conscious minds like ours. If that's the case, the number of simulated realities would vastly, unimaginably outnumber the one and only base reality. The number of simulated minds would be trillions of times greater than the number of real biological minds. If that is true, then from which population are you more likely to have been randomly selected? The tiny population of real beings in base reality, or the astronomically larger population of simulated beings? Statistically, the odds are overwhelming that any given conscious mind, including your own, is one of the simulated ones. This is the ultimate paradox. Our very existence, our ability to even ponder this question, could be evidence for its own unreality. If we one day create our own ancestor simulations, it would be almost definitive proof that we ourselves are in one. Are there glitches in the matrix we can look for? Déjà vu? Physical constants that seem suspiciously fine-tuned? Or is the simulation so perfect that it is, by definition, indistinguishable from reality? And if it is, does it even matter? The food is still nourishing, the love is still real, the pain still hurts. But the thought lingers, a nagging piece of code in the back of your mind. This entire universe, every star, every planet, every person, every thought you've ever had, might just be a line of code running on some post-human's hard drive.